Good day, my name is Nikita Guroz and I am a technical consulting lead at Cadgroup. Today I'm going to talk about a relatively new product, Nastran In-CAD, and demonstrate linear and nonlinear static stress analysis on a practical example. So first of all, I would like to introduce myself. I'm an aerospace engineer by trade and in the past was involved in a number of projects, so mostly related to finite element analysis. So I began my career as a stress engineer at the Boeing company and was working on 787 development project doing finite element analysis of aeroplane part wings, fixed leading edge and trailing edges in particular. Then I was a design engineer at General Electric and worked on assemblies of finite element models, or basically large-scale assemblies, and was doing structural analysis, fatigue analysis, and also simulation of collisions. And for a number of years I've been working as an Autodesk application engineer for different companies. So today I would like to do a real-world simulation. This model is provided by one of our clients, SS Rods, and was designed completely for a new vehicle they made. It was called Hot Rod. The main focus in this example is the lower suspension arm of this vehicle, made of aluminum 61, and let's actually take a look at the inventor model. So as you can see, that part is pretty important because it takes all the weight of the or basically fraction of weight of the car, and in this particular mechanism takes the vertical load through the steel insert we've got here and the connection to the wheel through this ball joint. Also it has got a pretty standard connection at the other end through rubber bushes, and also a rubber bush connects it to the vertical spring. When we open that part, you can see that basically there is no need to analyze the steel insert because it's a standard part, and steel is basically stronger than aluminum. But as this part was designed for this particular vehicle, we need to understand how it works and can it withstand the required loads, and if necessary modify the design before the product gets built. So the Nastran In-CAD, it's basically an add-on for Inventor. It's integrated with the Autodesk Inventor, and you can launch it from the same environments panel pretty much in the same way as you do stress analysis in Inventor. So here we've got this stress Autodesk Nastran button, and when I click on that, it opens an additional tab where we can get access to all features of the product. Also, the modeling or analysis tree is available in the model browser in the same way as we have access to the Inventor features. So first of all, as I mentioned before, we need to do a static stress analysis of the part, and in the list of analysis types, of course we can choose different types of analysis. The Nastran In-CAD has a very long list comparing to Inventor, and the linear analysis is just the beginning. We also can do normal modes, so calculate the natural frequencies, do the linear buckling, so basically calculate the safety factor when the structure loses its stability, and also, for example, do nonlinear static analysis or even nonlinear buckling. Then a few more advanced analysis types, such as transient response, nonlinear transient response, and fatigue analysis and thermal analysis. Basically, I just want to focus our attention today on linear and nonlinear static analysis. I think that many of you are familiar with the linear static because it's available in Inventor. However, the Nastran In-CAD has got more advanced tools and constraints comparing to Inventor. So the workflow is basically the same as in every FEA package, and the panels from the left to right represent a typical analysis workflow. So let's follow that particular workflow and start with our material properties. So as I mentioned before, this part is made of aluminium 6061, and here I've got the material properties, such as yield stress is 148 megapascals, the maximum tensile strength 241 megapascals, and also this particular aluminium allows pretty high elongation before the break, up to 25%. For the linear analysis, we probably need to know only two main parameters, the Young modulus and the Poisson ratio. And going back to the Nastran In-CAD, we can define the material properties in a number of ways. So basically, the material properties often comes with the model, because Nastran In-CAD is integrated with the Autodesk material library and Inventor material library. And when you assign material in the Inventor, it automatically copies properties from those databases. Also, you can load material properties from the Nastran In-CAD database. So if I open that, you can see that the list of materials in every category is pretty long, and you probably don't need to go to the other sources for those values. However, if you want to create your own material library for just the materials you use, often it's also possible to save your material properties in the data file. So let me open my data file and load the aluminium 6061 properties from there. As I mentioned before, the Young modulus is 68 or almost 69,000 megapascals. Then the Poisson ratio is 0.33, and as you know, we don't need to enter the shear modulus, because for the linear or isotropic type of material, it can be computed automatically based on the Poisson ratio and the elasticity modulus. Okay, so then once the material is defined, we need to double check our element types, and then also that the physical property is based on our defined material. So if I open the physical properties, you can see that the element type is set to solid elements. However, for different parts in the assembly, we can also use shell elements or line elements if required, and of course different material types as well. So from this particular analysis perspective, the properties are defined in the correct way, and therefore we can start work on our constraints. So in many situations, the constraints or loads could be not really adequate enough to represent parts in the assembly. And in this particular example, we need to simulate the revolution joint at those two ends, and also something similar in the middle at the connection with the spring. Therefore, I would like to use a quite interesting element which comes under the category of connectors, and this is a rigid body. The rigid body basically connects one vertex or point in a structure with a number of dependent entities, such as edges or faces, or basically nodes that are associated with those entities. To create this element, we need some reference geometry, and therefore I would like to close this dialog for a minute, go back to my model, and unhide a few sketches I prepared just recently to use them as a reference geometry for our model. So when I switch visibility of those cases, as you can see, we have here a couple of points, and also basically 2 points here at the center of the cylindrical face to be used as a reference for the element axis. So going back to the Nastran In-CAD, we can now use those points as a reference geometry for the rigid body element. So first of all, let's pick that point in the middle, and then pick those faces as dependent entities. So the idea of this element is an absolutely rigid connection between all nodes on the dependent face and the central point, or the master node here. In other FEA packages, the rigid body element is also called RBE2. However, there is another formulation of this element, or the element type, called interpolation, which is also called RBE3. On the other side, we have the other sort of connection. So it's basically connection through the rubber bush, and therefore we can use the same approach here, but change the rigid body type to the interpolation. So the main difference between those two is that interpolation element computes an average displacement of all points in relation to the master node, and therefore it works a bit more, or it behaves like a soft connection between the main area, between the master point and the dependent nodes, and does not restrict deformations in the dependent area. However, the geometry of this element is constant, therefore it still be categorized as a rigid or undeformable body. So the reference point for this element will be that point here, and of course the dependent region is basically a cylindrical face of our part. So then we need to create the same element at the other end. Again, a rigid body, type interpolation, point in the center as a master node, and also dependent area, the whole face. So then we need to think about the appropriate boundary conditions. The connection at this area can be categorized as a single supported, or the basically one direction supported point, and therefore I would probably prefer to use the simple constraint here, such as restriction in the y-axis, or on the other hand, let's probably use an element and another element type just for this particular example to constrain this point. If we go back to the connector creation dialog, you can find another interesting element here, spring. Spring, it's basically an element created, a linear element or line type element created between 2 points. So if I pick the master node of my rigid body and also just a point on a sketch, it automatically creates this virtual element, so then you can specify stiffness in different directions. This particular analysis is linear static analysis, so therefore we don't need to simulate the real behavior of the spring. It's okay just to constrain this point and then lock all the displacement of the master node, and we can do it by applying very high stiffness to the spring in the spring properties. So basically we can try something like 10 powered by 7 as a stiffness in all 3 translational degrees of freedom. So first 3 coefficients are responsible for the translational degrees of freedom, and then the other 3 coefficients are rotational degrees of freedom. So basically I don't want to fix rotation of this particular component here, because in the real model we don't have that connection at all, and we can just specify some sort of low, very low stiffness here, which basically would represent something like a ball joint or the spherical connection at this end. So then at the other end we can use similar approach with the other 2 springs. Let's just do some practice how we can use the spring elements as a virtual part, and for this purpose we can create an element between 2 points here, and then just use the next button, and under the same dialog create another element. So basically we can use the same properties for 2 spring elements. Okay, I would prefer to make it very rigid as well, just to constrain the all degrees of freedom, or use it as a rigid connector between single point and our rigid body element. Something like this. So basically what I'm trying to do here, I'm trying to create virtual parts, because sometimes there is no need to simulate the behavior of the made components. It's okay just to use different types of connectors and simplify the analysis, and also reduce the computing time. Then, following the typical workflow, we come to the constraints area. The constraints are basically very simple things, so we can create structural constraints or thermal constraints, And in this particular example, I would like to fix this point only in the translational degrees of freedom. So if I hit the pin button, it automatically removes constraints from rotational degrees of freedom. And basically this point is fixed in space, but it can rotate in all degrees of freedom. And then the other constraint I should apply to those 2 points. It should be probably another fixed constraint, but I would like to allow rotation around the axis. Therefore, let's untick the rotational degree of freedom around z-axis as it parallel to those axes of those cylindrical faces. If necessary, you can create additional coordinate systems and define your constraints in the way you like. However, in my example, the z-axis of the global coordinate system is parallel to the axis of that cylinder. That's all good, and when I hit the OK button, we basically generate 2 more constraints. And from this perspective, I think that it's enough. The part is fixed in all degrees of freedom, or in other words, we don't expect any rigid body motion. And it's time to apply loads. So if I go back to the main model, as you can see here, we have that steel insert, and that takes vertical load and also some horizontal loads. For the design purpose, we decided to apply 4500 newtons in the vertical direction and also 1000 newtons in z direction and x directions simultaneously. Plus, there is another load case, the ultimate load. The design load is different to the ultimate load because this is what we use in the design. However, to make sure that the part can withstand much higher loads or be more reliable, let's apply absolutely different safety factor and multiply our limit loads in 3 times to see how that part actually behaves under an extremely high loads. So going back to the analysis, we can select this face and just click on this marking menu, loads, and create a force load. As I said, 4500 newtons normal to the selected face. And then the next one should be the reaction force from the cylindrical insert, but it's not really a good idea to use a standard force, because standard force distributes the load across the whole surface. However, in this particular case, the force should be applied only to a half of the surface, and we know from the mechanical stress calculations that the maximum of this force is actually at the same point as the direction of our load, and therefore it is a good idea to switch to a different type of load called bearing load. So bearing load automatically computes the force distribution along the cylindrical face and basically represents the typical reaction force from a bearing or another cylindrical object. And as I mentioned, we need 1000 newtons in x direction and 1000 newtons in x direction, so x and z directions. As you can see, when I click the oh sorry, I need to select the region. When I click the OK button, Nastran In-CAD automatically computes that nonlinear force distribution along the face. Once we've applied all forces and the constraints, our model is ready for the analysis. So I would like to click just the Run Analysis button to let inventor on Nastran In-CAD generate mesh with the default settings, because for the first or preliminary analysis we don't need a very high accuracy. We would like to know basically where are the main points of interest and what are the results in general. So let's take a look at the analysis results. So for this particular analysis, the best result to check is one mesostress, because our design criteria is yield stress, and as was confirmed by a number of practical tests many years ago, the one mesostress predicts the yield point very good. Basically, it's good for the prediction of the yield point. So when I click display button, you can see that the deformed shape looks pretty good. So this exaggerated scale or exaggerated deformation demonstrates that we have some rotation around this point as expected. Also, the stress concentrators are located around the thinnest cross sections. And when we compare these results with our allowables, so basically for this material we have 148 megapascal yield stress, you can see that it's not what we need, and we need to modify the geometry in order to reduce stresses in this area. And in fact, it's not a really difficult thing to do, because all the forces and constraints and other basically analysis features in Nastran In-CAD are associated with the invented geometry, and at any time we can close the analysis, go back to our model and modify the geometry. So I think that we need to make the cross-section here a bit wider, and therefore I need to modify the base sketch and change the width here from 25 up to 29 millimeters. As you can see, that dimension is linked to the other side, and we basically update the geometry automatically. So now I need to finish my sketch. Inventor updates the model, and we can try another analysis cycle. So it's enough just to open the Nastran In-CAD, click Update Mesh, and rerun the analysis. The main advantage of linear analysis is that it takes a very short time to compute the results. So we can perform a number of, even dozens of iterations per hour, and optimize our structure immediately after the, we finish our sketches, so change the dimensions and so on. So let's take a look at results and check what's the current stress and our points of interest. That's much better. That's currently under the limit, so it's 137.4 megapascals. However, I need to make sure that this result is actually the same, that this result is reliable. And from my experience, I know that sometimes the mesh quality around the stress concentrator is not really adequate enough to represent the high gradients of stresses and other analysis factors. Also, we can see that despite the fact we use the parabolic elements, the mesh does not really represent the geometry in the right way, because by default it does not copy or move the mid-side nodes to the surface, and literally that particular fillet is not has not really rounded shape as it should be. Therefore, I need to change some settings, some mesh settings, and as we use the parabolic elements, we can also project the mid-side nodes to the structure. So with this option, Nastran In-CAD moves the mid-side nodes of our tetra elements to the face, and that creates a much more accurate mesh. Let's take a look at the result. As you can see, now the representation of that geometry is much better than was before. And also, in order to make sure that the result around the stress concentrator is correct, we need to do the mesh convergence study. So sometimes basically big elements or rough mesh does not have enough resolution to compute the load factors with the required accuracy. And the approach here is to reduce the mesh size in order to compare the two results. So if there is no change in the maximum or the stress in the area, we can say that the mesh resolution is good, and no other improvement is required. So to do this, we need to use mesh control. Okay, let me create a new mesh control. So add mesh control to our mesh settings and reduce size up to 2 millimeters on the selected faces. So this face, that face, and also those fillets we need to include in order to make sure that the mesh is good enough for those areas. So that face as well, and that one, and this one, and here, and that one as well. Okay, so then let's click OK button, update mesh, and rerun the analysis. In this case, analysis takes a bit longer than before because we have, I think, twice more elements and nodes. However, the linear analysis is still very quick. By the way, Nastran originally came from aerospace industry, and has got a very good and proven solver. So the as I mentioned before, we are now doing the mesh conversion study, and therefore we need to compare results from the previous simulation with the new results with more accurate and fine mesh. And as you can see, we've got a new maximum. First of all, the maximum is in a slightly different location, so it moved to this fillet, and the value is higher than it was before. As you remember, the original value was in the previous iteration was 137 megapascals, and it was under the allowable, but now it's 142, and it's higher than our limit, which means that we need to do another update of our design, and I think it's probably a good idea to increase this radius here to smooth the load between those two areas. Okay, so let's finish this analysis, go back to the original sketch, and change this radius from 20 to, let's say, 35 millimeters. So let's click Finish. Inventor automatically updates the design, and then the same steps. Update mesh to create new finite element mesh, and run the analysis. I think that mesh quality and mesh accuracy, one of the most important questions for all people that use finite element analysis. And the most important probably thing is the understanding of the principles of the finite element analysis. You need to think about the mesh as a number of very small volumes of material and a very simple approximation of the load factors within this volume. Therefore, if we have any loads or other factors that can potentially change the stress picture very rapidly from one point to another, you always need to think about more accurate mesh or much higher mesh resolution in order to represent those rapid changes. And as you can see here, we are talking about this particular thing. So that's why we need to maybe in the final analysis do another mesh refinement and try even smaller mesh size in order to make sure that the result is stable. It does not depend on the analysis on the mesh quality. As you can see, this little design change really helped us to improve the part, and our current stress is under the limit. We've got a really positive margin of safety. So let's take a look where that current stress concentrator is. Yes, it's now on the other side and it's under the limit. But what if we want to apply different loads, the ultimate case, where loads are 3 times higher than the limit load? In fact, the linear analysis is good because we can simulate different sub-cases or different combinations of load. So currently we have a number of loads here, under the subcase 1, and let's rename it to limit load. And after this, we can duplicate the subcase in order to analyze a different combination of load factors. So the limit load case, we can rename the copy of this limit load case up to ultimate. And then keep constraints and other components the same, but modify the loads and basically use copies of these loads with different values. Oops, sorry, copy. Copy, paste, and then copy, oops, copy, paste. So I created 2 more copies, and let's rename the vertical load to ultimate ultimate Y, and on this dialog we can also specify which particular subcase, or so we should include this load into the subcase ultimate. Okay, and then let's do the same with, oh sorry, I forgot to change the value. So as I mentioned, we need 3 times higher force, 13,500 newtons. And then the same we can do with a bearing load. Ultimate XZ, 3000 newtons and 3000 newtons, and also specify or choose the subcase to include that load into it. So when I click OK button, as you can see, we need to remove the limit loads from the ultimate subcase, and basically what we've got now, we have limit loads under the limit subcase. That's the first load case, and then we can simulate an additional one, the ultimate load case, with the same constraints but different load values. So if I click run, the Nastran In-CAD automatically simulates 2 load scenarios, and we can review and compare results between 2. So I think that if we apply 3 times higher load, it will be really hard to check the strength of this part, because the limitation of the linear analysis is that it does not change the material properties when we go over the yield stress. And in the limit load we were not far away from the yield point, so I expect extremely high values of stresses in the ultimate case. So if I click the design options, as you can see, just give me a second. If I go to results, from the drop down here we can switch between different results. So here are results for the limit load case, and here are results for the ultimate load case. And when I click options, you can see that stresses are extremely high. So we've got 366 megapascals stress in basically the same area, and it's basically higher than the tensile strength of the material. So we can't really say can this part withstand, or from the result you can see probably not. Therefore, to actually simulate the real world behavior of this part and include plasticity into the analysis, what we need to do, we need to switch the analysis type to linear, from linear static to nonlinear analysis. And that's very easy to do. You can duplicate the original analysis, or just go to Edit and change the analysis type from linear static to nonlinear static. Don't forget to tick strain in the output sets and click OK button. So the nonlinear analysis, it's basically a number of linear analyses. So let's remove the unnecessary load case from here, the limit load. So delete, yes, and keep the ultimate load on and the ultimate loads under the subcase. So if I click on the nonlinear analysis settings, you can see that the most important parameter is how many load increments are going to run. So basically the nonlinear analysis runs as a minimum 10 linear analysis and gradually increases the load from 0 to the maximum, to the 100% scale factor. And if the Nastran sees any changes in the material properties, so basically stresses, for example, higher than the yield, it updates material properties and runs additional analysis to see how the model behaves under the new properties. So therefore, before we run the analysis, we need to make sure that our material model is adequate to represent that behavior. And we need to actually go back to the material properties and see what can we do, or what sort of material model we can use. So I think that I need to say a few words about the material models available in Nastran In-CAD. In the previous example, we were using the linear material model. So as you can see, the it's a simple straight line or simple equation which connects the stress with the strain. Also, we can use nonlinear elastic material model for the nonlinear materials, and plastic materials, which is a quite common thing for all the metals, with where we've got linear segment and also nonlinear curve when we reach past the yield point. And plus we can simulate plastics, rubber with nonlinear material models. However, the nonlinear material models such as nonlinear elastic, nonlinear plastic, and nonlinear elastomers are not really good for our model for two reasons. First of all, we need a simple model, so we don't want to spend our time doing the material tests or checking the plastic properties of the material. And also the hyperelastic materials are not really suitable for the materials like aluminium. And from my perspective, the best way is to use the bilinear elastoplastic material model, because we know that beyond the yield point, the material curve can be approximated as a straight line. This material model is very good for the typical metals, or for the most of metals, if you want to analyze them beyond the elasticity limits. So therefore it's pretty easy to compute this hardening factor. That's why I would like to specify the elastoplastic material models, specify tangent modulus, and also set the initial yield stress with the yield criteriation, of course, the 1 meter stress up to our yield limit. So with this material model, we can analyze the material behavior beyond the elastic point and also simulate the material hardening effect. Actually, this analysis takes a much longer time than the linear one. And in this particular example, it took about an hour to compute the results. So basically, it doesn't mean that you need to sit and watch how it works. You can do some other things. And also, the good thing about Nastran In-CAD that it can utilize all your processor cores, so it works very fast and efficient. And plus, you can actually manage how many cores it utilizes. And if you have 4, 6 physical cores, you can continue work in another window of Inventor on your design models. You can check emails, do whatever you like, and run the analysis in background. So, of course, today, or right now, I don't want to run this particular analysis. We don't have time for it. But I would like to show you the results from the previous simulation. So here I've got the same model, and I performed the nonlinear analysis for this model just some time ago. So as you can see here, just a second please. As you can see here, the boundary conditions, elements, everything is the same as before. The only one difference is that the mesh resolution is even better here, because the non-linear material models and the plastic or areas of the plastic deformations in particular, they require very high mesh accuracy, and that's why I reduced the mesh size up to 1 millimeter here. So then if we look at the results, you can see that the nonlinear analysis performed 10 iterations, and the load factor at the end is 1, so 100% of the load. So then we can check 1 meter stress. Oops, sorry. Options, display. And the 1 meter stress. Alright, let me switch off the element edges, because we can't see the results because of them. So here, this is the area of the maximum stress, but this little spot here doesn't really tell us what are the actual deformations. As you can see, there are pretty wide areas where stress is actually beyond our elasticity limits. So all colors from yellow up to red, this is where we have plastic deformations. And the best result to review those effects is actually effective strain or plastic nonlinear elastic strain. So the strain factor, this is the most appropriate result to see for the plastic deformations. And as you can see, the maximum strain we've got is 5%. So and therefore that maximum elongation actually can be found in a completely different area. So that's the most problematic point here. And as you can see also that the areas with positive plastic strain are almost connected to each other, which means that once that blue area or zero plastic deformation disappears between those two spots, the whole area converts into a plastic joint. So we are currently balancing at the edge between the workable model or workable part and the complete structural failure. So you can see how significant deformation is if I switch the deform options from the exaggerated scale to the actual scale. So imagine that if we really apply a very high load to this part, you can see how it bends. So give me a second. I just want to display all the bodies and just compare the results with undeformed body with the actual scale factor. So this is a real deformation, or basically 12 millimeters deflection at this point here. Of course, it's not allowed in the normal design, but it gives us very good confidence that under 3 times higher load this part still works. Yes, it bends a little bit, but guarantees very high margin of safety in extreme situations. So that particular result so we can only obtain this result in the Nastran In-CAD because it's advanced analysis type, and that's available as many other analyses in Nastran In-CAD. So that's probably all what I want to demonstrate you today, and it's not, in fact, as you can see, it's not a very complex analysis. However, of course, if you want to learn those things, we're absolutely happy to provide you with our trainings. So I just want to say a few words about it. So our training system is designed to give you the confidence in the analysis, or basically teach you up to the level so you can solve your day-to-day problems with confidence and know that the model is good enough, that your assumptions were correct, the mesh quality is right, and you can trust those results. So basically the typical training course is divided into 4 phases. First of all, we teach the basics of FEA. It's like not really complicated stuff, but we basically talk about the mesh, the approximation, interpolation, different boundary conditions, how they work, how the contact elements work, and how to apply them and refine the mesh if necessary. Then, of course, it's the comprehensive training around the Nastran In-CAD user interface. So how to launch the model, how to get access to different settings or results. And then the third phase, it's on-job training. So basically, we always ask our clients to provide us with their models, their design challenges, and then during the training course we can solve the actual design problem, go through all the decisions required to make the model, analyze the results together, and understand how it works. Also, we offer the additional remote support because we know that even after the course, people can find some challenges that were not really covered by this, or they have some doubts about what they do. Therefore, we can quickly connect to your computer using our remote support system, discuss the models, check your results, and provide you with an advice. So our vision is to help you to solve all your design challenges by providing you with the custom training courses. And if you have any questions, please feel free to call us or find our website, and we're absolutely happy to discuss all your design problems, all your design challenges, and we're absolutely sure that we can give you the extremely good quality of our services so you can achieve good results and solve all your design challenges. So thank you very much for your attention, and I would love to see you on our next webinar and other sessions. Thank you very much, and goodbye.